Section 4.5, linear approximation and differentiables. We're going to start looking at some problems. So if we start off by looking at number 8. Number 8 says that if you go 1 mile in 63 seconds, it asks us to give us an approximate average speed here, and then what is the exact speed for this interval of time. So once again, as we're considering this problem, we got to be thinking about, we got units in here, what are some easy conversions within, what do we all have going on. So one of the best ways to look at this is to be thinking about 60 seconds would be a base unit for 1 minute. So if we consider this to be 60, we now look at how much over are we. If we're over, we're going to subtract off, because once again, if we're going over, we're actually going to go slower than what that 60 seconds would be telling us. So 60 minus 3 equals 57 miles per hour. Okay? Because once again, when we start thinking about this speed, we want to convert to miles per hour, because I don't know a car that has miles per second. That would be very confusing for most people. Our cars have miles per hour, so that's our normal speed we work with. So this is just that approximation of what this speed would be without actually doing a bunch of work in this. Now, how would we find the exact amount? Well, if we think about it, we have 1 mile in 63 seconds. Okay? So we want to convert this to be hours. So we want our miles per hour. So we have to multiply by seconds up here. Now, a direct conversion from seconds to hours is 3,600. So there are 3,600 seconds per hour. So if we take 3,600 and divide by 63, we get 57.14 miles per hour. Boy, we're really close. Now, once again, this linear approximation, like we had mentioned in the very end of our previous lecture there, the closer we are to having an interval of 0, so once again, we had an interval added in of 3 as a change in our x. We consider this now, as this gets closer and closer to 60, this is going to get more and more exact. As we get further away from 60, well, this is going to have some issues within here. But this is also a good thing as you're driving along. Basically, if you count the number of seconds for 1 mile of travel, kind of you can start approximating what your speed is going to be. Now looking into our true linear approximation that we'll be working with, number 16. So on number 16, they tell us that f of x equals x over x plus 1. And then they tell us that a equals 1 and f of 1.1. Okay, so as we're considering in here, we're trying to basically break down this complicated formula into a linear approximation, okay? Because a linear function is easier to calculate, you know, our mx plus b, it's easier to calculate out than our overall complicated function. So if we think about this, we are trying to figure out this formula right here. So let me put it in red. We're trying to figure out our linear approximation, and this linear approximation is f of a plus f prime of a times x minus a. Okay? So we're trying to fill in this function right here where this is a value, and then this is going to be an x minus a. So if we think about it, basically we're kind of using our point slope formula on this, because we're going to have our slope of a value at a given point, and then that overall interval that we're working with. So let's start off by finding that f of a. So f of a would equal 1 over 1 plus 1, because once again a is 1, so I'm substituting 1 in for my x. So we get 1 over 2. We got to find f prime of a. Well, in order to find f prime of a, we got to find f prime of x. So f prime of x equals, we have a function over a function, our quotient rule. Okay, so we have low d high minus high d low all over the square of what's below. Okay, so bringing this down here because I want to save this room here for my linear approximation. Bringing this down here, this is x plus 1 minus x over, we have x plus 1 the quantity squared. So this is 1 over x plus 1 the quantity squared. So now we take f prime of 1, because f prime of a. So here I can go like this, f prime of a equals f prime of 1. So we have 1 over 1 plus 1 squared, so that is 1/4. Okay, so if I kind of come back here and start filling in what I have, we have our linear approximation is f of a, which was 1/2, plus f prime of a, so we found f prime of x, then we substitute in the 1 for the a then, so that's 1/4, times x minus a, and a was 1. And so now what we see here is we see that the linear approximation, just simplifying out, we have 1/2 plus 1/4 x minus 1/4. So our linear approximation of x is 1/4 x plus 1/4. Okay? So what does this mean? This means now that, so this was our part A answer right here. Okay, so this was all the work that went into part A. Part B asks us to graph this in the linear approximation graph. So you can type this into your graphing calculator. You can type this into your graphing calculator. Have your window highlighted from, I would say, 0.9 to 1.5. Would kind of give you an approximation here, because once again we have a is 1, and then we're working with 1.1 for a value in here. So that's kind of where we want our answers to be at. Part C then is going to be asking us, well, hey, what is the approximate value for f of 1.1? Okay, so we can use our linear approximation, so I'm going to use approximately. I'm going to take 1/4 times 1.1 plus 1/4. If we type this into our calculator, we get 0.525. Now, if we were to consider what's going on overall, let's bring in my calculator here, I could have plugged that into my original equation, had that 1.1 over 1.1 plus 1. Okay, and we see we get 0.54. Okay, now do consider this. Okay, so consider this problem as it would be without this calculator. Okay, could I take 1/4 of 1.1 plus 1/4? So this is 0.25 and 0.25. 0.25 times 1.1, I can easily multiply out by hand. If I had to come back here, I would have 1.1 divided by 2.1. How easy is that to divide out? This is much easier. Okay, so when you had to calculate out and work with all this stuff by hand, issues always came in. So do realize that the linear approximation does aid us in the fact of how do we approximately work with these things. And basically it's just following this formula and finding what these values would be. Looking at a differentiable now. So let's look at number 42. Okay, so on number 42 here, it tells us that f of x equals sine squared x. Tells us to consider the following functions and express the relationship between a small change in x and the corresponding change in y in the form dy. So we want this form, I'll change over to my red color here. dy equals f prime of x dx. Okay, so we got to look at this. We got to figure out, well, what's going on overall, what's happening with the overall function. So we got to find f prime of x first off. So if I go f prime of x, now do realize this is a chain rule. We have a function squared right here. So we have a function within a function. So if I work with my inner function, the derivative of sine is cosine. So we have cosine x times the derivative of something squared would be 2 times that something to the 1 power then, in which that something was sine x. So cleaning this up, I have 2, I'm going to go sine x cosine x for a function here, in which then now that I found this derivative, to write it in this form, rather than stating that it's f prime of x or that it's dy dx, where if I said y equals, I would write it this way now and state that dy equals 2 sine x cosine x dx. Okay, and this differential part really comes into play in our last section in this chapter. We start talking about the antiderivative and how do we start going backwards. Also in next chapter when we get into our integrals, it's a very important role in understanding the differentials on here. But do realize it's just following this formula in which we just are breaking this derivative up. So instead of stating y equals and taking the derivative of y with respect to x, we're saying we got a function, this is our function, the derivative of the function here, and now we're putting it in terms of y as the derivative itself.